Let's solve a problem involving the calculation of thermodynamic work, which takes place at a constant pressure. So here we have a problem. Refrigerant 134A is contained in a piston cylinder assembly, and it's initially as a saturated vapor. The refrigerant slowly heated until its temperature is 160 degrees C. During the process, the piston moves smoothly in the cylinder. For the refrigerant, evaluate the work in kilojoules per kilogram. So here we have a piston cylinder oriented vertically. And we can see that the pressure inside the cylinder is really determined by conditions outside of the refrigerant. It's determined by the atmospheric pressure bearing down on the piston, plus the weight of the piston distributed over its area, bearing down on the refrigerant. Now we were given that the atmospheric pressure is 1 bar and that the piston had a weight of 471.1 newtons. So we can calculate the area of the piston, which we've done here. It's pi over 4 d squared. And the pressure in the cylinder is therefore the atmospheric pressure plus the weight of the piston divided by its area. The atmospheric pressure is 1 bar. And the weight of the piston is 471.1 newtons. We have an area of the piston of 0.00314 square meters. We need to convert units that we know a newton per square meter is a pascal. And there are 10 to the 5th pascals in a bar. So the pressure inside the cylinder is the pressure of the atmosphere, which is 1 bar, plus the pressure created by the weight of the piston, which is 15 bars. So the pressure in the cylinder is a constant 16 bar. Now this is my usual storyboard for a problem involving any process. I like to draw a schematic, and here we've got a vertical piston cylinder, and the boundary is around the refrigerant. And so only the refrigerant 134A is the system. The system, or the cylinder and the piston, are not part of the system. We know that an expanding gas defines positive work, and energy being transferred into the system via heat transfer is a plus Q. Here's the data we were given. That state 1 is a saturated vapor, which means its quality is 1. And the final state is at 160 degrees, and this being a constant pressure process, P2 is equal to P1, and we already calculated that to be 16 bar. Now here's a PV diagram of that. We've got our vapor dome, and a constant pressure line at 16 bar would go right through here. And we know that state 1 was on that constant pressure line at the saturated vapor line. So here's state 1 right here, and state 2 is out here at the same pressure, but a higher temperature of 160 degrees C. To model this, we're declaring that this is a closed system, that changes in kinetic and potential energy are negligible, and of course it's a constant pressure process. Our interest is finding the work in kilojoules. Now we know that for a process such as this, the work is the integral of PdV. And previously we've already solved this integral for a constant pressure situation. And we know that work is just the pressure times the change in volume. Well, we can also go to the saturation table at 16 bar, and we know that the specific volume of state 1 is the specific volume of a saturated vapor. And so we have that value. And then from the superheat table, we can find the specific volume of state 2. The properties that define state 2 are 16 bar and 160 degrees C. And the table provides this value of 0.02017 cubic meters per kilogram as the specific volume. So the work then is just the pressure, 16 bar, times the change in volume. We have to convert bar cubic meters to kilojoules, and 1 bar cubic meter is 100 kilojoules. And we calculate a work for this process 1-2 of 12.9 kilojoules per kilogram of refrigerant within the system.